Greetings Physics 2001, Section 102 students. This is lecture 24. It's the second of two lectures on thermodynamics, and it's actually the last lecture with any new content. So the final two lectures will just be review, helping you review for the final exam. So general reminders, you have an assignment due on Friday. Note we're calling that assignment 13 because it was the original assignment 13, but don't pay attention to the name. You have an assignment due on Friday, and this week you have the usual help rooms and SI stuff. The most important thing is that exam 3 on Lon Kappa, there is a thing called information for exam 3 that's posted on Lon Kappa. So again, we're going to do exam 3 and also the final through Lon Kappa as a timed exam. Exam 3 is going to be open starting at noon on Monday, April 20th. It's going to close at 6 p.m. on Tuesday, April 21st. Once you start it, you only have 90 minutes to complete it. Okay, so any 90-minute window that fits within this Monday the 20th at noon through Tuesday the 21st at 6, any 90-minute window that fits in there works. The content is going to be rotation, harmonic motion, fluids. So anything that happened online, any of the online material, so stuff after spring break, through fluids is fair game for that exam. That's what it's going to focus on. Now, technically, there may be some content from much earlier in the semester. For instance, you aren't allowed to forget, forces and kinematics because it's physics. Everything's tied together. We're going to focus on those topics covered, basically stuff that wasn't covered on the previous two exams through fluids. So to finish off thermodynamics today, we're going to discuss cycles and heat engines, and that will finish things up for the semester, except for the reviews. So a cycle, we talked about this last time, but didn't go too much into it. It is a transition that forms a loop on a PV diagram. So again, you have this diagram where you have the pressure versus the volume. Any given point is a state, so that's a snapshot of our gas. So our gas at A has this pressure corresponding to that vertical position, and the volume corresponding to this horizontal. And you can transition from state A to B by just increasing the volume, B to C by just decreasing the pressure, C to D by decreasing the volume, and then back D to A by just increasing the pressure. So for going from one state through a bunch of others back to the same state, that is a cycle. So it forms a loop in this PV diagram. So in this full cycle, we go A to B to C to D to A. So let's calculate the net internal energy change. Well, you have an internal energy change from A to B, B to C, C to D, and D to A. You sum all of those up, the net internal energy change is 0. Because if I start out in some state and I wind up back in the same state, there's no net internal energy change. Okay, so this equation can be useful sometimes. The net work, again, you just sum the net work from your, in this case, 4 steps. Work A to B, B to C, C to D, D to A. If you had 5 or 6 steps, you would add those as well, right? And then similarly, you can sum your net heating is the heat added to the system for transition A to B, B to C, C to D, D to A. Okay, so the point here is when we say net for any of these things, we're just talking about adding up the work or the heat for each step in the transition or change in internal energy. And it's just an important point that for a cycle, the change in internal energy is 0. So for example, so we have A to D, A to D and back to A, right? The change in internal energy is 0. So that's the 0 net change in internal energy. In this case, the net work is going to be greater than 0. So how do we figure that out? Well, let's look at the transition from A to B. The work from A to B, we sum up the area under the curve. So it'd be a big old rectangle that covers this whole space here. That is the work, and it's positive because we're going from small volume to large volume. Okay, so we have a lot of work, a lot of positive work done by the system going A to B. B to C, we don't change volume at all. So there's 0 work for B to C. Similarly, later on when we go D to A, there's 0 work again. So now let's jump back and consider, well, what about C to D? You're going from a larger volume to a smaller, so negative work is being done by the system. And the area under the curve, we just take the area underneath this line, that is smaller than the area under the curve from A to B. So when we add up our total net work, we have A to B is some large positive number, A to B is some large positive number, B to C is 0 because there's no change in volume. C to D is a smaller negative number. It's negative because you go from large volume to small volume, less area than A to B, so smaller negative number. D to A is 0 work, no change in volume. So you're going to have positive net work because the area under A to B is greater than the area under C to D. Okay, so positive net work, and remember from the first law of thermodynamics, the change in internal energy of the system is equal to the heat added to the system minus the work done by the system. Because we have a cycle, the change in internal energy is 0. So then for our cycle, in this case, we know that the heat added to the system, the net heat added to the system, is equal to the net work. So that's always going to be true for a cycle. But in this particular example, the net work is positive, and therefore there's positive heat added to the system for this example. If you were to reverse the arrow direction, so let's say instead you did A to D to C to B to A. Let's say you went in the opposite direction. Then you'd have a small amount of positive work for D to C, a large amount of negative work done by the system from B to A, and so your net work for the cycle, if you go in the opposite direction, is in that case going to be negative. And so that means you're going to have negative heat added to the system, which in everyday life we'd say that the system releases heat to the surroundings. Let's do a question here related to cycles. So in this picture that we have, the heat added to the system for A to B is positive. Okay, we're just telling you that. And the change in internal energy from B to C is positive. So the question is, what is the change in the sign of internal energy for the step C to A? So you have to keep in mind a couple things. This one is actually a little bit complicated, right? Remember that the change in internal energy over the whole cycle is 0. So if I do delta U for A to B plus delta U for B to C plus delta U for C to A, that is going to be 0. Okay, and you also need to keep in mind this equation that comes from the first law of thermodynamics, that delta U is equal to Q minus W. So the change in internal energy for a given step is equal to the heat added to the system for a given step minus the work done by the system for a given step. You can use that. So please do pause and think about this one because it's actually a little bit difficult of a question, and you need to really make sure you can work it out on your own to make sure you understand this business of calculating change in internal energy and works with cycles. So pause the video, please. Take a minute and work this one out. I'm going to assume that you've paused and you've come back, and you've figured out that the change in internal energy for step C to A needs to be negative. Okay, so why is that? So remember, for our cycle, the net work over the cycle is 0, and that's going to be the change in internal energy, not the network. The change in internal energy over the cycle is going to be 0, and so that means the change in internal energy going from A to B plus change in internal energy B to C plus change in internal energy C to A. Sum those up, that is 0. Okay, and we can use this first law of thermodynamics either for the net work over the whole cycle, or we can use it just for a given step. So the change in internal energy for step A to B, this is equal to the heat added to the system for step A to B minus the work done by the system for step A to B. And the area under the curve here for step A to B is 0, right? There's no change in volume. So the work for step A to B is 0, So we actually know then that the heat added to the system for step A to B is going to also be equal to the change in internal energy for step A to B. We're told that the heat added to the system for step A to B is positive. Therefore, the change in internal energy for step A to B is positive. Okay. So now we know what the sign of the change in internal energy for step A to B is. We're just told that the change in internal energy from step B to C is positive. And so now we know the sign for A to B and the sign for B to C. They're both positive. We need to add something to that to get 0. Okay, so then we know that the net change in internal energy for C to A needs to be negative. I have two positive numbers, I add something to that, and I need to get to 0. Therefore, this C to A needs to be a negative number. Okay, so here are just some examples of engine cycles, just to kind of give you an example of what does a practical engine look like on a PV diagram. We'll really just focus on the Carnot cycle because it's the maximum theoretical efficiency engine. So it's useful to understand the limiting case, how well can an engine run. But these other ones are examples of real engines that exist in real life. So if you have a 4-stroke engine, that's the Otto cycle. If you have a sort of one lung engine with that special piston, that's the Stirling cycle. And then you instead can think about what does a diesel cycle look like. So this is for a diesel engine. So it's like your Otto cycle that you'd have for a 4-cylinder combustion engine, but the compression provides the heat for the fuel ignition in a diesel cycle. Okay, so this can be a 2 or 4-stroke. So if your Otto cycle is like your usual internal combustion engine, your diesel cycle, that's like a diesel engine. The Stirling cycle, my dad had this old crummy sailboat growing up, and that had a Stirling engine in it. So these things do exist in the wild. And the Carnot cycle, again, it's really particularly useful because it's this maximum efficiency engine, and we'll go over some examples for that. So now let's take the concept of changing internal energy and work and internal energy in the system and consider engines. So if we want to understand engines, we need to use thermodynamics. So let's first consider a heat engine. So what is that? It's generating work from a temperature difference between a hot and a cold reservoir. So we're not going to worry about the magic of this engine. We have an engine, okay? It's a black box. And we're going to just consider the sort of no efficiencies involved is basically what we're doing here. So if we have a high temperature reservoir and a cold temperature reservoir, we can extract work that is a heat engine. And so for instance, let's say you have a flame providing heat and a cold stream providing the cooling, and this magical engine is in between the two that can produce some work in principle. So you have heat flow from the hot to the cold reservoir, that's Q sub H. You have heat flowing from the hotter engine now to the colder reservoir, that's Q sub C, and then work is produced. Okay. So this is accomplished right by heat transfer. That's you don't get free work. The work comes from the heat transfer to and from the reservoirs and the engine. You can reverse the heat engine, so you can use work to create a temperature difference. So think, for instance, an air conditioner or a heater, and we'll talk about these cases. Okay, so heat engines, they operate in a cycle, and so the change in internal energy for a heat engine is 0 because it's true for any cycle. So you don't need to worry about, we talked about some engines and cycles on the previous slide. Don't worry about which one it is. It doesn't matter because for all cycles, the change in internal energy is 0. And the first law of thermodynamics applies. The change in internal energy of the system, which is 0 for the cycle, equals the heat added to the system minus work done by the system. So for the engine and for all cycles, the heat added to the system over the course of the cycle is equal to the work done by the system over the course of the cycle. Okay, your high temperature reservoir, this is adding heat to the cycle, where the low temperature reservoir is removing heat. So for the heat engine, if we want to know what's the heat added to the system, the net heat added to the system, it's this heat flow from the high temperature reservoir minus the heat flow to the low temperature reservoir, Q sub H minus Q sub C. Okay, so therefore, the work done by our engine is equal to the difference between the heat flow from the high temperature reservoir to the engine minus the heat flow from the engine to the low temperature reservoir. Okay, so the work is Q sub H minus Q sub C. For reasons that we may or may not appreciate, while I think this is much more practical and much more intuitive, often what you see is that the heat added to the system from the high temperature reservoir, the heat flow from the high temperature reservoir to the engine, that is equal to the work done by the system plus the heat flow from the engine to the low temperature reservoir. So why would you write it this way? This is sort of a statement of energy conservation, right? What goes in must come out. So perhaps you would prefer to remember this equation, that what goes in must come out. So Q sub H is W plus Q sub C. The other way to think about it is in terms of the first law of thermodynamics. And in that case, you really just want to keep in mind that for a cycle, heat added is equal to work done. And the heat added is going to be the difference between flow from the high temperature reservoir minus flow to the cold temperature reservoir. So perhaps this equation is more useful. They say the same thing, right? It's just a little bit of algebra, and it depends on how you want to think about it, energy conservation or thermodynamics. So the efficiency, this is what you get out over what you put in. Makes sense, right? So the efficiency of your engine, of your heat engine, is the work done by the engine divided by the heat flow from the high temperature reservoir. You can see algebraically by plugging in these previous relationships, this is equivalent to the difference between heat flow from the high T reservoir to the minus the heat flow from the low T reservoir. We just plugged in this definition of work. Or with some algebra, that's equivalent to 1 minus the heat flow to the cold temperature reservoir divided by the heat flow from the high temperature reservoir. So, what do you need to know here for your heat engine? You need to know these two equations that are boxed in. Again, instead of the one on the left, you could use this one on the right. They're equivalent. I prefer this. The work done by the engine is the difference between these two heat flows, and the efficiency is 1 minus the heat flow to the cold reservoir divided by the heat flow from the hot reservoir. Okay. So let's do a question here. So what is the efficiency of a heat engine that pulls 8,000 joules from the hot reservoir and then it expels 6,000 joules in the form of exhaust? So for instance, let's imagine that you burn a bunch of fuel to get 8,000 joules, and then you have to get rid of the exhaust gas, and that's 6,000 joules. So what's the efficiency of this heat engine? So pause. You can assume that you've paused and you've come back. Keep in mind here, what are we given? We're trying to find efficiency. We know what's been put in, and we know what comes out, right? So it's 25%. We can solve for this. So efficiency, what you get out divided by what you put in. So the efficiency is the work done by the engine divided by the heat added to the engine from the high temperature reservoir. You can work through it and say, okay, the work you get out, that's the difference between heat added and heat removed. So that's Q sub H minus Q sub C. And so we can take the difference between our 8,000 and our 6,000 joules, divide that by 8,000 joules. And when we do that, we get 0.25, so that means 25%. Alternatively, you could have jumped straight to the equation that it's 1 efficiency is equal to 1 minus Q sub C divided by Q sub H. So then you'd get 1 minus 6,000 over 8,000. That 6,000 over 8,000 is 3/4. So 1 minus 3/4 is a quarter. So you get 25% again. Again, same equation, so not surprising. So, and indeed, that's just what I'm saying down here at the bottom of the slide. So if you minimize the ratio of heat removed to heat added, that's going to maximize the efficiency, which it makes sense. What goes in needs to come out. To maximize efficiency, you'd like work to be the thing coming out. Okay, the exhaust doesn't really help you in terms of what the engine's doing. So you'd like to minimize that ratio of heat removed to heat added to maximize your efficiency. How much heat is added and removed, like how does the heat removed relate to the heat added and the work? That's going to depend on the type of transition. So do you have, what type of transition do you have? And we've gone over some of those. So let's treat this theoretical but extremely useful case called the Carnot engine. So this is our maximally efficient heat engine. Okay, and it's pictured on the right here on our PV diagram. If we start out at A, we have an isothermal expansion, then an adiabatic expansion, and then an isothermal compression, and then an adiabatic compression. So this is the best possible heat engine. So for the best possible heat engine, then we need the disorder of the system and the surroundings to not increase when transferring heat. Okay, it's impossible, practically speaking, but we can imagine it and you can approach it in real life. You also need your hot and cold reservoirs to be completely infinite. So taking heat from the hot reservoir doesn't change its temperature. Adding heat to the cold reservoir doesn't change its temperature. This might sound dumb because how do you add heat to something and not change the temperature? But it turns out it's close enough to true in real life that you can often use it. If you have a really massive object and you add a little bit of heat or you remove a little bit of heat, you don't really change its temperature that much. So that is not that crazy of an assumption. So for the Carnot engine, then we have the ratio of the heat removed to the heat added is equal to the temperature of the cold reservoir divided by the temperature of the hot reservoir. This is only true for the Carnot engine. This is for the maximally efficient engine case. And so then for the efficiency, we can substitute the temperatures in instead of the heats. And so for the Carnot engine, the efficiency is 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. So remember, this is for the maximally efficient engine. You can never have a larger efficiency than this for a heat engine. Okay, it's always going to be equal to this at best or lower. So pretty much always lower. You need to pay attention to the temperature has to be in Kelvin. Okay, you got to be using SI units here. Otherwise, this does not work. Okay. And also, because of the third law of thermodynamics, you cannot reach absolute zero for your cold reservoir. You can never have TCs equal to 0. So therefore, you can never have a 100% efficient engine. Okay, it is not possible. There is no perpetual motion machine. You always have to lose some of that energy just due to inefficiency. Okay, no matter what. So let's do a practical question. Let's remember what we know about our Carnot engine, and that's the maximally efficient engine. And let's put that to work here. Okay, so your crazy uncle fancies himself as an inventor, and he claims to have created an engine that draws heat from a reservoir at 375 Kelvin. It does 5,000 joules of work per second, and it expels 4,000 joules of work per second into a cold reservoir of 200, that's at 225 Kelvin. So the question is this possible? Okay, so calculate the efficiency based on the heat added and the work, and then calculate the Carnot efficiency based on the temperatures and compare the two. I'm going to assume that you've paused and then you've come back. And you'll see that no, your crazy uncle is indeed crazy as we suggested. Tell this guy to go away. So what's the claimed efficiency? Well, we can use the statement about how much work was produced by the engine we need to know how much heat was added to the system. Based on energy conservation, the heat added to the system, right, that's equal to the work done by the system plus the flow to the cold reservoir. So then the claimed efficiency was 5,000 joules divided by 9,000, which is 0.56. Just based on the work being done and the flow, how much exhaust comes out. You can figure out what the efficiency is. So that's or what it's claimed to be. Now let's do our Carnot case. So for the Carnot, okay, what's the temperature of our cold reservoir and the hot reservoir? Well, that's 225 Kelvin divided by 375. So we subtract that from 1 and we get 0.4 is the maximal efficiency that you could have possibly have. So the claimed efficiency is better than the theoretical maximum, which isn't possible. So these basically the claimed efficiency is wrong. One of those numbers is made up somehow. Okay. So in all likelihood, the work done is a lot less than you think it is, or perhaps there's a lot more exhaust produced than you think. Okay. So now let's reverse our heat engine, and will be used for cooling, and that's known to its friends as a refrigerator. So you put work into your engine, and that enables heat flow to go from the cold reservoir into the engine, and that enables heat to flow from the engine to the higher temperature reservoir. So we're putting in work, and that's what allows us to do this. We've reversed our heat engine. Okay, so for instance, that's how a refrigerator works, right? You're trying to keep the cold stuff cold. So how does a refrigerator actually work? You might be curious what it's actually doing. Is you basically take a motor and you compress a refrigerant that's going to heat it, okay? The heat is then given off to the environment on the back of your refrigerator, so that's why the back of the fridge is pretty hot. You then allow it to expand, which it then cools just before it enters the fridge. So now you have this colder fluid flowing through, and heat is then going to flow from the warm food inside the fridge to this very cold fluid, because heat goes from hot to cold. And so your fluid has warmed up, and then you basically use the engine to compress it, and that heat is allowed to transfer to the outside environment. So that's how a fridge works. You need refrigerant to do this. So there's a little motor compressing fluid and circulating it all the time. So as before, this is still true, right? It's an engine, and therefore you're going through a cycle, and therefore the change in internal energy is 0, and therefore the net work is equal to the work done by the system. Or yeah, I said that wrong. The net work is equal to the heat added to the system. So again, heat added is heat from high T to engine minus heat from the engine to the cold reservoir. So that's still true. So how well your refrigerator is performing, that's going to depend on how much it's cooling divided by how much work you put in. So we define this thing called a coefficient of performance. And so that is how much heat flow is coming from the cold stuff into the engine divided by how much work you're putting in. Makes sense. How much work do you got to put in to take the heat out of your hot food and put it into the refrigerant? Basically, that's the coefficient of performance. You can rewrite this, getting rid of the work, right? Because the work is directly related to the difference between these heat flows, we can restate this solely in terms of heat flow, as we've done here. And you can define a Carnot refrigerator. So the perfect hypothetical, theoretical, perfect refrigerator. And for that, it's as before, you substitute in temperatures instead of these heat flows. So what do you need to know here? You need to know this coefficient of performance. It's what's the heat flow from the cold reservoir to the engine divided by the work you put in to achieve that heat flow. And I didn't box it, but you really should also know the Carnot is as before, you're just plugging in temperature information in place of heat. And this is the theoretical perfect refrigerator. So let's work on our refrigerator question. So we have a refrigerator. It removes 60,000 joules of heat from hot food placed inside the refrigerator. The coefficient of performance is 3. We eventually want to know the amount of heat that's going to be exhausted into the room. Okay, that's what we're going to work towards. Because you need to know that from an engineering perspective. If you're going to put a fridge in a house, is it going to catch fire to the stuff behind it or not? So we want to get there. The first question, though, is what quantity does the 60,000 joules represent? Is it Q sub C, Q sub H, or work? So pause, come back. Hopefully you've drawn this to try to figure it out. And you'll see that 60,000 joules, that represents the amount of energy that must be removed from the cold reservoir, in this case, our hot food. All right, and so here is a picture, for instance. We have our work being input from electrical energy. Heat is being removed, perhaps by this compression and expansion of fluid, as we talked about previously. And then exhaust goes out. And so what we're talking about is the heat removed from the food, so that's going to be Q sub C. Okay, so let's keep going. So we know that 60,000 joules is Q sub C. So question now is, what is the amount of heat that's going to be exhausted into the room? So if you're going to design a room, you need to know this. Can you put that fridge in the corner or not? Are you going to melt the stuff behind it? So what's the heat moved into the hot reservoir? So I'm going to assume that you have paused and that you have come back. And you'll see that it is 80,000 joules. So what do we need to know here, right? The coefficient of performance, right? That's the ratio of how much heat you remove divided by how much work you put in to remove that heat. So you use that to get the 80,000 joules. So the coefficient of performance, that was stated as 3. That's going to be equal to this Q sub C that we've removed, 60,000 joules, divided by the work. Okay, so the work then is 20,000 joules, but we're not done yet. We were asked how much heat is exhausted. We're not asked how much work was put in. So our refrigerator had to consume 20,000 joules of work. It had to put that much in. So now we have to solve for the heat, the exhaust heat. So this is where our concept of conservation of energies may be useful. What we've put in has to be equal to what comes out. And so the flow from the refrigerator engine to the outside environment, the exhaust, this needs to be equal to the heat we've pulled from the food plus the work that we've put in. So that's sum that up and you get 80,000 joules. Okay, so remember, you're not allowed to forget anything. So let's take some stuff that we learned earlier. So about work and power. So again, your refrigerator, it removes 60,000 joules of heat from the hot food inside. You have this coefficient of performance is 3. If the power of the motor is 200 watts, how long is it going to take to cool the food? So you could look at your refrigerator, look at the documentation that comes with it and figure out how much power it's consuming. You'd have to assume some efficiency, or it'll probably tell you the efficiency. Then you'll know the power that this thing has. So then you can calculate, well, how long is it going to take for us to cool our food? So I'm going to assume that you have paused and that you have come back. Recall that we found that the work to cool the food is 20,000 joules. So using that, we can figure out that it's going to take 100 seconds to cool this food. That's because power is energy divided by time. That's what I meant when I said you're not allowed to forget anything. Power is just defined as our energy over time. It's 200 watts. We determined that the work that you got to put into this fridge to do this cooling is 20,000 joules. So we can solve for the time, and it's going to take 100 seconds to cool this food, which is not too shabby. Now let's think about one more type of engine. It's a heat pump. So we've again reversed our heat engine, but in this case, we're going to heat with it. Okay, so instead of trying to take heat from the food and pump it into the outside environment, we're going to try to take heat from the outside environment and pump it into your room. Okay, it's kind of imagine standing on one side of the refrigerator or the other. The one, are you near the cooling side or the heating side? That's basically the heat pump. You're standing on the heating side. And indeed, your home may have a heat pump. Um, they tend to work at our latitude and below. They don't work well at cold temperatures, so you don't really see them. I lived in Michigan for a long time in northern Ohio. You don't really see them here, but you do see them in southern Ohio and in the south. So again, what we've done here is we've put in work to create a temperature difference, and we can use this to be a heater because we're standing by on the warm side, and the heat flow in this case, instead of heat being sucked from the food, we're basically sucking heat from the cold outdoors with our heat pump, and we're achieving that by putting work into the heat pump, into this engine. So again, it's true that this is an engine. The engines undergo cycles. The change in internal energy of a cycle is 0, and therefore the net heat added to the system is equal to the net work done by the system. The net heat added is equal to the heat flow from the high T reservoir to the engine minus the heat flow from the engine to the cold environment. That's still true. So again, we can define a coefficient of performance for your heat pump. In this case, it's how much heat are you getting out compared to how much work you're putting in. So the coefficient of performance is going to be this heat flow from the engine into your house, basically, divided by the work. How much electrical energy are you consuming in your engine? That's your coefficient of performance. And I should mention the stuff that we just covered for the refrigerator, right? That basically all still applies. The equation from the first law of thermodynamics applies. You can use all that information. So let's try to identify different or heat pump here. So each drawing shows a hypothetical heat engine or a hypothetical heat pump, and it shows the corresponding heats and works. Only one of the 5 scenarios is physically possible. So which is it? So note that we've said how much heat is going from hot to cold, from between the engine and the cold reservoir, from the hot reservoir to the cold reservoir, how much work's going out. And note that there's different arrows here, right? So we can either have a heat pump, heat engine, or a refrigerator, depending on where all these arrows are going and the work. So sit and think about what you've learned about heat pumps and heat engines. Which one of these is actually possible? Remember, energy has to be conserved. What you put in needs to come out. So Q sub H has to be equal to Q sub C plus W. I'm going to assume that you have paused and that you have come back. And you find out that C is the only physical one here. So remember, energy is conserved. What goes in has to be equal to what comes out. All right, there's no such thing as a perfect engine. So the thing is, for E, you might say, like, well, let's just run through the different cases here. So in this case, A, we put 300 in and 500 comes out. That doesn't make sense, right? So that one's not true. B, what are we doing? We're putting in 400 and we're removing 400, but that's not how it works, right? That's what it looks like in terms of the arrows, but remember, Q sub H has to equal to Q sub C plus W. So we have 700 here, that's not equal to 100, so that's wrong. So then jumping to D, again, we add these two, that's 500, that's not equal to 300, that doesn't work. In this case for E, we add 400 to 0, well that does equal 400, so that seems like it makes sense, except there's no such thing as a 100% efficiency engine. It's not possible. This would be a 100% efficient engine. And so therefore this one's not physical, doesn't exist. So then let's go back to C. We add these two together, Q sub C and the work. We get 500, and then the Q sub H is 500. And so indeed that makes sense. So that is your physically possible heat engine. These all seem similar, but can be kind of different. I just want to summarize a heat engine versus a heat pump versus a refrigerator in this summary table. And I encourage you to use this on an equation sheet. Okay, this is basically what you really need to know about your engines, pumps, and refrigerators. So we have a column for the device, what that device is basically doing, what the basic concept of how it works rather, what it's actually doing, what are we paying for here, and then how good of a job is the device doing its job. So a heat engine, this is just going to be a natural flow of heat, and that's going to be used to do work on surroundings. So what does this provide? The heat engine provides work. So what are we putting in? How do we pay for this work? We pay for it with heat flow from the high temperature reservoir. That's how we pay for it. And the inefficiency comes in that there's some heat exhaust. That is not work. So how well of a job is it doing? It's the net work divided by the heat added to the engine. That's your efficiency, and that's got to be less than 1, somewhere between 0 and 1. And the theoretical maximum performance is 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. So going on to a heat pump, what is this? This is an unnatural flow. You have flow of heat from cold to hot, and you create this unnatural flow by work from the surroundings. So what does this heat pump do for you? It adds heat to, for instance, your house. How do you pay for this? You pay for it with work. So electricity, for instance. How do we know how well the heat pump is doing? That's with the coefficient of performance. How much heat do you get out of this heat pump divided by how much work do you got to put in? And what is the theoretical maximum performance? That again is you plug in temperatures instead of heats. That gives you the Carnot coefficient of performance. And then finally we have the refrigerator. What is this? This is an unnatural flow of heat. So from cold to hot, taking it from the hot food, putting it or from your cold inside of your refrigerator to the hot surroundings. So how do you create this unnatural flow, or what is it providing rather? It's removing heat from food, for instance. How do you pay for that? Because it's unnatural, work from the surroundings. So for instance, electricity. How well is your fridge, how well of a job or how good of a job is your fridge doing? That's defined by the coefficient of performance. So that's how much heat you're sucking from the inside of the fridge, from the food, divided by the work that you're putting in, for instance, via electrical energy. And the optimum performance, again, is Carnot. And so here you have 1 divided by the temperature of the hot reservoir divided by the temperature of the cold minus 1. So this summary table, if you write this down or print it out and have it handy and you've practiced a few of these problems, then you should be good to go for engines. And this actually completes the lecture on thermodynamics and completes the new content for the class. So after this, there will just be review for the final exam, but this is everything for the semester. As a one reminder, you will have listened to this likely before the exam, exam 3 on Monday. This content, thermal physics, thermodynamics, is not on exam 3. It will be on the final exam.